In section 9.1, we're going to be solving equations that have radicals in them. And so just as you might expect, if we are trying to clear a radical, we're going to use an exponent to help us do that. So for example, if we have a square root, we're going to raise it to the second power. If we want to clear a cube root, we're going to raise it to the third power. And that pattern holds 4th root to the 4th power, 5th root to the 5th power. And that's because those are inverse operations that undo each other. One thing we do have to keep in mind as we're solving equations with radicals, if we have an even index, and by even index, I mean like a square root, a 4th root, a 6th root, and so on, we have to check our answers because we might end up with what are called extraneous solutions. Extraneous solutions. And basically those are just solutions that we get that don't work in the original equation, so they're not actually a solution. Okay, so let's look at a couple of these problems. We have the square root of 7x plus 2 equals 4. To undo that square root, we're going to square it. Whatever we do to the left side, we do to the right side. Squaring and the square root cancel each other. And I'm left with 7x plus 2 equals 4 squared, which is 16. If we move that 2 over, we get 7x equals 14. If we divide both sides by 7, we get x equals 2. All right, so to check this, we're going to plug it back into our original equation, and you can do this in your head, in your calculator, however you want to. We're just going to see if it works. We have the square root of 7x, or 7 times 2, which is 14, plus 2 equals 4. 14 plus 2 is 16. Square root of 16 is 4, so we get 4 equals 4, which is true. So that means that was a solution. Okay, on the next one, we have the cube root of x minus 1 equals negative 4. Since we have a cube root, we're going to use a cube or an exponent of 3 to cancel that. Whatever we do to one side, do to the other side. Cube root and cubing eliminate each other, so I'm left with x minus 1 equals negative 4 to the third power, or negative 64. If we get that x by itself by adding 1, we get x equals negative 63. And on this one, we actually don't have to check it. It's not an even index. It was an odd index, so we know that x equals negative 63 is a solution. All right, for 444, we have the 4th root, so we will have to check our answers here. To get rid of that 4th root, we raise it to the power of 4, and I end up with 3x plus 6 equals negative 3 to the 4th, which gives me 81. If we solve this, if we subtract 6, we get 3x equals 75, or x equals 25. All right, if we plug this back in to check it, I get that the 4th root of 3 times x, or 3 times 25, or 75, plus 6 equals negative 3. Or the 4th root of 81 equals negative 3. Well, if we type the 4th root of 81 in our calculator, I'm going to get 3, which does not equal negative 3. So that tells me that x equals negative 20, or x equals 25 was not a solution. It was extraneous. So we have no solution to this equation. Okay, so sometimes we don't have only a square root by itself on one side. If we have a square root with something else on a side, the first thing we want to do is isolate that square root. We want to get that square root by itself. So to do that, I'm going to move that x to the other side. Then I end up with the square root of 4x plus 1 equals 5 minus x. Okay, be careful when we square this. The left side, simple enough. The square and the square root cancel each other. We get 4x plus 1. The right side, though, don't forget that 5 minus x squared really means 5 minus x times 5 minus x. So we've got to multiply out those binomials. If we do that, we're going to get this, 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 and this. I'm going to go ahead and do the multiplication and simplification kind of in one step. I'm going to get 25 minus 10x plus x squared once we multiply and simplify. Okay, because we ended up with an x squared, to solve this, we're going to have to solve by factoring, which means we need to move everything to one side and set it equal to 0. So if I move this 4x over, it goes with those x's. This goes with the 25. Let me scoot that down a little. So I'm going to get 0 equals x squared minus 14x plus 25. Don't forget, when we're factoring, these are the ones we actually prefer to factor. All we have to do is think of two numbers that multiply to give me this, add to give me this, and I made a mistake here. That should be 24. 25 minus 1 is 24. So two numbers that multiply to give me 24, add to give me negative 14. That's going to be a negative 12 and a negative 2. So if we solve both of these equations, we're going to get x equals 12 and x equals 2. All right, we're going to come over here and check them. We have to check both of our equations. If we check x equals 12 first, we're plugging it into our original equation. So I get 12 plus the square root of 4 times 12, or 48, plus 1 equals 5. We have 12 plus the square root of 49 equals 5, or 12 plus 7 equals 5, which is not true. So x equals 12 is not a solution, it's extraneous. For the second one, if we check x equals 2, I've got 2 plus the square root of 4 times 2, which is 8 plus 1, which is 9, equals 5. Square root of 9 is 3. 2 plus 3 does equal 5. So x equals 2 is fine. That's a solution. X equals 12 was not. Okay, so here we actually have two square roots in the problem. So we're going to see, first of all, if we can get rid of them at the same time. To do that, we're going to have to move one to the right side, keep one on the left side. So I'm going to rewrite this as the square root of 3x minus 8. If I move this one to the right side, it's going to be a positive square root of x. When it looks like this, it's pretty nice because when I square both sides, it automatically eliminates both of my square roots. So I end up with 3x minus 8 equals x. If we move our x's to the right side, I get negative 8 equals negative 2x. If I divide by negative 2, I get x equals 4. We're going to plug this back into our original equation and just check it. To check it, I'm going to have the square root of 4 times 3 is 12 minus 8 minus the square root of x, or the square root of 4, equals 0. All right, we get the square root of 4 minus square root of 4 equals 0, or 2 minus 2 equals 0, which is true. So that is a solution. Okay, sometimes though, when we have two square roots in our equation, we can't get rid of them both by squaring both sides the first time. So let's see what happens on example 447. Same thing like the last one, I'm going to move this to the right side. So I get the square root of 2x plus 1 equals the square root of x plus 1. I can't combine those two things because they're not like terms, so I write it just like that. So I'm going to square this side, square this side. Left side's simple enough. We just get 2x plus 1. The right side, though, I'm going to actually come over here to the top. The square root of x plus 1 squared means the square root of x plus 1 times the square root of x plus 1. And let's see what we get when we multiply that out. Square root of x times square root of x is x, plus 1 square root of x, plus 1 square root of x, plus 1. If we simplify this, we get x plus 2 square root of x plus 1. All right, so that's what my right side is, x plus 2 square root of x plus 1. Notice we did not eliminate all of our square roots, so we're going to have to try to isolate this piece and square it again. So if I move my x's to the left side and my 1 to the left side, let's see what we get. This actually cancels out and gives me 0, and I just get x equals 2 square root of x. All right, so we are going to square both sides to get rid of that square root. So I get x squared equals, if we square this, 2 square root of x squared, I'm going to get 4x, because that really means 2 square root of x times 2 square root of x, which gives me 4x. Okay, so now to solve this, let me scoot it up here. I'm going to factor this. I'm going to move everything to the left side. I get x squared minus 4x equals 0. Take out your greatest common factor of x. If we solve this, we get x equals 0 and x equals 4. We would then take both of those, plug them back into our original equation to check them. And for the sake of the length of this video, I'm going to let you guys do the checking, but they both should be true. And we're going to skip example 448 for this video.